Okay, you want to go ahead and take over?
Okay, so it seems like the troops are already a little tired after lunch. So no hard proofs in this one. I think a lot of really interesting and important and fascinating concepts, but I'm not going, so I will mention a few proofs, but then from each proof I will try to single out one or two small things that I think may be interesting and worthwhile for you. Okay, so again, we're talking about this subject of high-dimensional combinatorics, and really, for permutations, we have perhaps a more round story to tell. Here we have more things to tell, but perhaps it's a bit more groundwork that we have to prepare. So we have to start with a definition. So let me say perhaps one thing, one caveat. There's going to be an elephant in the room. The elephant's name is topology. But don't worry, it's a very friendly animal. It will not hurt you. And so I will only here and there, you don't need to know any topology to follow this, absolutely not. But for those of you who have some background in that, here and there where we come to close encounter with the animal, I'll just point out and say that, okay, this is how topologists would consider it, but there's really absolutely no need to. Okay, so this is the basic definition. Perhaps the name sounds somewhat impressive, but it's really a very simple and very natural combinatorial object, and I'll explain the connection with combinatorics, with geometry. We will be speaking completely combinatorially. So a simplicial complex, everything is finite. It has a set of vertices V, as usual, and this is, X is just a collection of subsets of V, which is closed down. That's it. That's the whole definition. So what do I mean? If A, so A is a subset of V, and it's a member in this collection. So under these two assumptions, that A is a member in this collection and B is a subset of A, the conclusion is that B is a member as well. Okay? And a little terminology, don't worry, this is really very simple, and if you never saw this, this is it. I mean, there is nothing complicated here. Members of X are called, I think this is perhaps, the other one is more visible. Huh? So no kid. Members of X are called faces or simplices. That's where the name comes from. You'll see in a second how. And if A is a face, then we associate a dimension which is just the cardinality minus 1. So think about it for a moment. It makes perfect sense. A point, cardinality 1, has dimension 0. A pair has dimension 1. It's an edge, and so on and so forth. And the dimension of X is the highest dimension of a face in X. Okay? So really make sure, I mean, it's always discouraging when you're in such a bunch of super clever people to, but really now don't be shy. Make sure, this is really crucial. If you don't feel comfortable with this definition, then you're in trouble for the rest of the lecture. So just make sure you're with me. It's really a very simple object, but we really need it. So this is crucial, that you understand this.
So if you think of a polytope, each face should be a simplex, then.
For example, but I want to what is a one-dimensional simplicial complex?
Graph.
Very good. But let's just make sure that we're all on this point. It's a graph. That's the same as a graph. Why? So we have the usual terminology that we're used to. We have a finite set of vertices. Faces are 0 or 1 dimensional because the dimension is 1. So, and so they're of the vertices. And the 1-dimensional faces are just the edges. And what is this condition? That if you have what is this condition? If you have an edge, then of course the 2 vertices are there too. Okay. So a graph is a 1-dimensional simplicial complex. Okay.
Regarding your comment,
yes.
In the higher dimensional case, it's a case of it's a combinatorial version of a polytope where every face is simple.
It's a simplicial, yeah, a simplicial polytope. Yeah, but I don't even want to assume that people know that, and I will not need it. But let me explain why this. So I don't want to go into the history. Also, I don't know it well enough. But this used to be a very important object in topology in the early years, and then they somehow took a different direction. I don't want to get into this, but it's really, for combinatorialists, it's really a very, very natural kind of thing. But just why? So why? What's the geometry here? Were people or are people interested in this kind of thing in geometry? Because, for example, that's a picture of a 2-dimensional simplicial complex. So it has these vertices. It has the 2-dimensional face 1, 2, 3. And of course, by the definition, it has also the 1-dimensional face 1, 2, the 0-dimensional 3. This, you have here 3 1-dimensional faces, 2, 3, 2, 4, 3, 4, and this one. Okay. So that really explains why it's such a basic geometric object. Because if you really interpret simplices to be really geometric simplices, so a triangle is a 2-dimensional simplex, a tetrahedron is a 3-dimensional, and you just create them and you glue them together in the right way. This gives you a way to represent geometric objects, potentially quite complicated geometric objects. And so just as a comment, why did they fall out of favor in the eyes of the topologists? Because they have more efficient ways of encoding geometric objects, CW complexes and so on. But the great thing for us is that this is completely combinatorial and we can think about it. Okay, so that's a simplicial complex. So the big story or the big plan that I'm suggesting, and certainly we didn't start with us, we'll come back to older things, is, see, it's really, I've been around long enough that when I started to be a student, I remember being asked by even teachers, why are you interested in combinatorics? This is, what's a clever guy like you doing in a place like this kind of thing? And of course, now students hear this and it sounds strange, but combinatorics is a fairly modern field. And by now, I think we've gathered enough knowledge and information and depth that it makes perfect sense to ask, can we somehow take what we've acquired and take it elsewhere? So combinatorics and graph theory, we've benefited from other more classical areas of mathematics for so many years. We can start paying back. I mean, many things like this already happen. And in particular, one thing which is, I think, really a place where combinatorics can really affect, or what we've learned in combinatorics can affect other areas of mathematics, is the probabilistic method. It's very easy to look at random combinatorial objects. It's much harder to look at random objects in other areas. And this suggests a way of doing this. Okay, so what this suggests is to develop, so if I'm looking at graph theory, two of the most highly developed parts of graph theory, so this which perhaps I will mention one small thing at the end, extremal graph theory. I mentioned it when I spoke about locality and so on. It's a huge area and deep and powerful. So can we take ideas from there and study them here? And what I'll mostly be talking about today is random graph theory. And again, with the great success that we had with this field, I mean, this suggests, can we develop a good theory of random simplicial complexes? What are the interesting phenomena? Are they, a priori, it's not clear. Perhaps the whole thing is just, you grind through the machine again, you get the same thing. But as you'll see, no, it's very, very different. And one thing that I hope those of you who were in the previous lecture, it's one thing that's really very nice here is that when you go up in dimension, many things which are completely obvious and boring and so on, you just tell them to undergrad, become completely unclear and very fascinating. And so this is the main thing that I want to talk about. So in the previous lecture, I mostly mentioned one collaborator, my student Tzur Luria. Here there will be quite a few more, and I hope to do justice and mention each of them when the subject comes. So this is what we're going to do throughout most of this lecture. Speak about some first steps that were taken in this direction, in developing a theory of random simplicial complexes. That's what we'll be spending most of the time doing. So on this I had many great partners, but certainly the first steps were done with Roy Meshulam. So now let me explain. So I don't want to even assume that people here are. I want to assume that everyone saw what GNP is, but I don't want to assume that people remember or know precisely. I'll remind you what we need to know about. Michal is online. What can you do? This you didn't explain to me. You said B and everything becomes black. I mean, it's only, this is through the back door. Okay. 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 Good. Okay, so let's start a little bit about, I mean, it's mostly going to be on the board, but as you understand, I have 2 or 3 slides to show you at some point. This is why I have it on. Okay, so we want to speak about GNP. This is, of course, the grandfather of random graph theory. Mostly, it was started by Erdős and Renyi in the late 50s, early 60s. And I think it revolutionized the whole way we think about discrete objects. So, but you have n vertices, and for each pair of vertices, independently and with probability p, you put an edge, and with probability 1 minus p, there is no edge. And you can do everything with any p, but most of the interesting stuff and what we will be doing is p, which depends on n. And if you want to summarize what the most important discovery, conceptually, if you don't want to get into the details, what we've learned from the theory of the theory of GNP is the phenomenon of thresholds, which is again a wonderful subject, worthy of a lot of work, but lectures and so on, I will not get into this. But the fact that phenomena of this sort tend to arise very abruptly, and at least I should mention one name here, Ehud Friedgut, who did his thesis with Gil, and he did some marvelous things about thresholds, but just to, okay, so what did Erdős and Renyi do in the fundamental papers? Okay. So, question, as a function of P, how likely is a graph in G and P to be connected? Okay, so for this I can show you one slide. This is a student who did a project with me, did it on the computer, and here it is. So let's say this is, n here is 100. And in fact, this is not precisely G and P. It's a cousin of G and P, and these different models are related to each other in very well understood ways. So let me explain the exact experiment. This is what Erdős and Renyi called the evolution of random graphs. Instead of picking every edge, you sequentially, you start with n vertices, and you sequentially throw in edges at random. And this tells you, so when you add a new edge, one of two things can happen. Either it will connect two distinct connected components, or it will fall in the same. So he repeated this many times, and this is the probability that in step X, you are connecting two different components. And you see the behavior of this. Okay? And eventually it goes down to 0 when the graph becomes connected. Then every edge is going to. So that's a very typical thing. And the fact that this has this threshold general frame of a threshold is a general phenomenon. So now we want to understand the threshold for connectivity. So theorem, Erdős and Renyi, 1960 or something. The critical P for connectivity is ln of n over n. Okay? So this has two things. I mean, it can be stated in very, very precise forms, and this is understood to a fantastic detail. But just to tell you the strongest form, let's say, there are even stronger things than this. I will tell you in a minute. If omega of n tends to infinity with n, then if my p is ln n minus omega over n, then almost surely G is disconnected. And if p is ln n plus omega over n, then almost surely it's connected. This is, the first part is really easy. Because from coupon collector, you see that if p is smaller than ln n over n, then not only is the graph disconnected, it has isolated vertices. So that's very easy. And what requires some work, but by now it's really fairly easy, is to show this. Okay? So really, connectivity is perhaps the simplest non-trivial graph property, and you could ask, is there an interesting high-dimensional analog of this? So what is the notion of connectivity? What do we do with these things? And as usual, and in fact as it was also with permutations and so on, this can be viewed in the realm of graphs in many different ways, and the whole thing is to find the way which gives you, and there is, so that's already one interesting point to make, which I alluded to before. With graphs, it's completely clear what it means for a graph to be connected. With a higher dimension simpler, by the way, I will almost exclusively speak about dimension 2, because again, almost all the phenomena are going to be clear, and the questions and the difficulties are going to be. So just that we have a terminology between us, that also simplifies the language. So we have vertices, edges means edges in a graph, and the two-dimensional faces that I just call faces. Okay, so we have three kinds of objects. Okay. How do you define, give you a collection of triples and pairs, every pair? When do you refer to such a thing as being connected? So first of all, one simplifying assumption that I'm going to assume throughout, which is certainly not crucial, but this is a choice that Meshulam and I did. So we're going to assume. So sometimes I will speak about D, but most of the concrete things I will do with D equals 2. We are assuming a full D minus 1 dimensional skeleton. So I'm assuming that all the faces of dimension D below D, strictly below D, are there. And the only random thing is which D-dimensional faces we're picking. In the case of graphs, the vertices are all there. Which edges are you picking? This is by no means the only interesting model. That's the model we at the moment understand the most about. That's the only thing. So when we want to have an analog of GNP, then what Meshulam and I introduced is the model. So we pick D faces independently and with probability P. So just make sure that you see that for D equals 1, that's exactly GNP. Okay. So now we want to understand what connectivity means. And there is more than one way of doing this, more than one interesting way of doing this. Something that I'm not going to get into at all. So this is, here I'm winking to the elephant. You can ask about simple connectivity for those who know what that is. So that's a very natural. I'm not going to go into this, but I have to mention it. Simple connectivity threshold, studied and almost perfectly determined in work by Babson, Hoffman, Hale. But I'm not even going to tell you what that means. I'll just have to mention that there is many more. There is not one definition. There are a whole bunch, in fact, infinitely many different definitions, and they're all interesting. And I'm going to speak about one which is particularly interesting and amenable to analysis and so on. So how are we going to define what connectivity means when we talk about, let's say, two-dimensional simplicial complex with a full one-dimensional skeleton? So let's go back to graphs. We're trying to get inspired by the situation of graphs, and let's look at this using linear algebra. So what does GNP look like? Well, there is this inclusion matrix of the singletons versus the pairs. So what is this? The columns correspond to all the pairs ij from 1 to n. And this column contains, this is numbered I. This has two ones, one in I and one in j, and zeros elsewhere. Okay. This is this is the matrix that corresponds to the incidence matrix of the complete graph. And what do we do in GNP? We select a random subset of the columns independently with probability P. And then we're looking at the matrix and we're trying to understand. So how does the matrix tell us?
I'm probably getting ahead of myself here, but so is there a reason you're doing 1, 1 and not 1 minus 1?
It doesn't matter. So okay. I'll come back to the.
Okay.
Yeah, it's a good question. I'll make a comment on this in a minute. Okay. So let's do it if you want like this. That's fine. Doesn't matter which. But we'll see in a second. But how do we? No, in fact, let me stay with the ones. I'll comment on this momentarily. But how do we see? So now I give you such a matrix. Let's say this is how many columns. This is the incidence matrix of a graph. You're looking at the incidence matrix of a graph. How can you tell whether or not the graph is connected? So this is the incidence matrix of a graph. How do you tell, using linear algebra, whether the graph is connected or not? So let's look, this is A. How do you tell if G is connected or not? By considering the left kernel of A of G. So let's see, well, let's understand this thing. First of all, so now I'm doing everything, and this is coming to, in a second, to your question, Ben. I'm doing everything, my linear algebra of the field with two elements, okay? So the left kernel of AG certainly contains the all one vector. Why? If you're a GF2, every column has two ones over GF2, that's 0. But in fact, if I did any other field than I did plus and minus 1, that would still be the case. So, and by the way, that we already see that there is a choice here, more than one natural definition. For example, we can do the whole thing over different fields. Or if you know how to do this, then even over groups or rings, or there is a whole variety, and that's also part of the story, that there is one more than one definition. That's always there, and G is connected if and only if this is all there is just this one vector. Right? Because if it's disconnected, you could have in the left kernel the indicator function of any connected component. Okay? So this is how linear algebra tells you whether the graph is connected or not.
That's true, right? So if you put the 1 and the minus 1,
Right. The same thing would work over any field. The convenience about F2 is that minus 1 is 1, and so I don't have, things become a bit simpler, but what do I do with all these people? Now you'll soon find out who all my friends are. Okay. Yes.
I don't see why, so if you are doing it over GF2,
Yes.
so why don't you get any cancellation and get something else? For instance, if you have like a cycle where everything, like you have, let's say, connected component and you go out of it from the cycle.
Look, we're doing GF2, right? So vectors are just 0, 1. So a vector is just a set of vertices. And a column, when do you get a 0 in a column? If both vertices are in the set or none of the vertices? When do you get a 1? If there is one vertex in the set and one outside of it. So a connected set, I mean, if the graph is connected, every set has edges going outside, right? So this is, okay. So this suggests a definition that works also more generally. So at least we are now able to formulate the problem completely and see what we get. So this suggests now the problem that we want to solve. So just to simplify matters, I will stay with F2. Things are a little simpler there, but you can do the same thing. I will make a comment about what happens over other fields. So what's the problem? Now we are starting with this matrix, pairs versus and if I get kicked from home, you'll tell them that it was during a talk. I couldn't take the calls. That you didn't see. What do I do? Oh, yeah. Am I going to get in trouble? Okay, it's my wife calling. Okay, good. So, you'll be my witnesses. Okay, so we're looking at pairs versus triples against the inclusion matrix. So this is the triple IJK. There is one in IJ, IK, and JK. 1, 1, 1, and the rest are zeros. We do the same thing. We pick at random every column independently and with probability P. And we ask, so the question is, what is, so we consider this as the trivial left kernel. We'll have to have a word, this will become a little more complicated here, but certainly not bad. What is the critical P For the event, there are no non-trivial vectors in the left kernel. So first we have to explain to ourselves what are the trivial ones, to rule them out. Let's say I do everything over the field with two elements. Unless I'm saying anything else, for the moment everything will be over the field with two elements. Much of it goes through to other fields, but just to that simplifies some technicalities. No. I will come back to other fields, but for the discussion, everything is the field with two elements. So what are the trivial? What are the trivial vectors in the left kernel? You see, if you saw any topology, then you must have seen this thing, whatever that means. And what this means in our case is that if I take, it's a very easy thing to check, that if I take these two matrices, and I multiply them one by the other, I get the zero matrix. So in particular, all the row space of this n by n choose 2 matrix is contained in the left kernel, this matrix A. So that's always there. And non-trivial means other than that. Okay? Just think about it. What was this one? This is the n choose 0 by n choose 1 matrix. So it's just the all ones vector. So this is really a special, this is the same thing again. So this is what we're asking. What is the critical P for which these are the only things in the left kernel? Okay? Now let's see. You remember that in the other Shreni, what was the thing? That it was ln n, the critical P was ln n over n. Why? Because this is a guess at least that would make sense, that below this, not only is the graph disconnected, it has isolated vertices. So what do isolated vertices look like when we're looking at such a matrix? The vertices, it's a row that's completely zeros. And then you get, of course, a non-trivial vector in the left kernel, namely, just take this row. Take the indicator of this vertex. So if here, in the n choose 2 by n choose 3, it so happens that we get a row of zeros, an edge that is not covered by any face, then the answer is, and if you do the exact same coupon collector argument, if P is less than 2 log n minus epsilon over n, then I will say it's disconnected in the sense that there is a non-trivial left vector in the left kernel. Not only this, even in the sense that there exists 0 rows. There exists an edge which is not covered by any face. We haven't we didn't choose any, we haven't selected any of the faces that contain it. Please.
So the two definitions are not equivalent, that any
Which?
edge, so one natural definition of not being connected would be that there are edges which are not covered by faces.
But that's like an isolated vertex. Of course, if there is compare this with being connected versus having no isolated vertices. So of course, if you have isolated vertices, you're disconnected, but the two are not equivalent. The two are not equivalent. They're the same here. Okay, so having a 0 row is a sufficient condition to being disconnected, the vanishing of the first homology in this case, but they're not equivalent. So what Meshulam and I proved is that the analogous thing holds. So in topologies, in the language of topologists, this is how you write it, is P, which is 2 ln n over n. The same thing. So of course, the main part, as it was with graphs, the main part is to show, the easy part, I told you, it's really just a very simple thing. The main part is to show that if P exceeds this, so the main part is to show that if P is 2 ln n plus little omega over n, then almost surely no such vectors in left kernel. Okay? So just
to get an idea of a way that would give me a probably suboptimal bound on P. I just want to make sure I understand. With the idea of U, I would take. I'm trying to get a feel for what is the row space of this matrix even going to look like?
Oh, okay. The row space of this is something that's very easy. You know what? Again, you are a step ahead of me. I will return to this in just a second. No, I will. It's a very good question, which I will return to in a minute. But let me just say one thing, because I promised to speak about other fields. So, Meshulam and Wallach, Meshulam's PhD student, Nathan Wallach, did this for other finite groups of coefficients. Same thing. So in particular over any other finite field. And very recently, just a few days ago, I'm sorry, I should have learned the name. There are 3 authors, perhaps some people here know. So Hoffman, Kale, and my apology for not remembering the name of the third person, just a few days ago posted on archive. If you know what that means, they showed that the threshold over the integers is order of D. In general, this 2 in general dimension is D. That we also know the same thing. So they showed that the right order of magnitude also with integer coefficients, but let's not even go into. Okay, let me try and give you just a little feel. So as I promised not to do any hard proofs, let me just give you one item from my work with Meshulam on how, and just a little bit to think about how to go about proving such a thing. Okay. So let's see. We are trying to understand. We are trying to understand the left kernel, right? I refer to it a little inaccurately as this is my complex, just the triples. Because since I have a full one-dimensional skeleton, the only thing that matters is which 2-dimensional faces I have. Now, we're trying to understand the left kernel of this. So we want to understand if this is A, we're interested in non-trivial solutions for this, right? And again, just to simplify matters, let's say that we're over the field with, you're so tired, I'm really sorry for you. I'll try, I'll do my best. So how do you think about it? What is such an X? We're over the field with 2 elements. As you see, this simplifies many things. So X is a 0, 1 vector. It's a 0, 1 vectors that the indices correspond to edges, to pairs. So such an X you might as well think of as a graph, right? X is an indicator. The way we should want to think about it is X is an indicator function of a graph. Okay, good. What does this mean? So you take any triple. So corresponding to X is a graph G. And this means that for every chosen triple, so if F is a chosen face, F meets G evenly. This is a bad notation, but you'll understand, is 0 mod 2. In other words, it's either 0 or 2. So what we really like to understand is the situation. So I think of X as a graph, and B of G. So now I haven't, I don't look at this. As in general, it's the collection of triples, faces, that meet G oddly. 1 or 3. Okay? So essentially the basic equality that we want to prove, there is still something critical that I haven't told you, but we want an equality that looks something like sum over G acceptable. I'll explain this in a minute. Of 1 minus P to the B of G, we want this to be little o of 1. That's the meaning. So with P, that's the key lemma. A key lemma. A key lemma says that if P is bigger than this 2 ln n plus omega over n, then such a thing occurs. Okay? That's the expected number of columns here, or faces that were selected that would go against this equality. Okay? So, but what is acceptable? You see, we understand there is a subspace of the left kernel which we really want to mod out by, which we really don't care about. Which means if you give me G and you give me a U so give me G and give me U in the trivial kernel, then whether G is in the left kernel is equivalent to G plus U in the left kernel. In other words, you can change, you're allowed, when you're considering these candidates to be in the left kernel, you can modify them by XORing with any trivial member in the. So somehow what I want is to select from any such choice. So these are just the cosets of this subspace of the trivial vectors. I want to select a canonical member. From every coset, I want to select a canonical member. So now I have to answer your question, what are the trivial vectors in the kernel? What do they look like? Or in other words, what is the row space of this? So that's very easy to tell. Each row here, what's the row space of this? Each row is just a star. All the edges that contain a given vertex. What happens if I add up 2 such rows or any such set of rows? What I get, again, remember that graphs here I think of as vectors here, I think of them as graphs. So it's exactly something like this. So I partition the vertex set into 2 parts. It's a complete bipartite graph on such a thing. So these are my trivial vectors. And so now this allows me to select what I want is a canonical choice of a member in cosets, in every coset of the row space of this matrix. This is what I need to do. So the choice is really very simple. You see, you have a graph, and this is one candidate that you can XOR with. So which U will I choose? I can always make sure that in this particular cut, by XORing, if necessary, with these guys, I would like G to be a minority here. So if G is initially fewer than half of these edges belong to G, I'm happy. If they are the majority, then I'll XOR, I'll complement, and I'll get. So I can guarantee, and that uniquely determines this canonical member, that G is minority in every cut in 1 to n. That I can guarantee. And such a G is considered acceptable. And then you get this, then this is the lemma that you prove. I will only tell you one more little thing about a key step in there. So this is the kind of thing that we want. So what works for us is if this number is big. We'd like this number to be big, and so a sublemma of this that we prove, and I just mentioned it. My initial plan was to prove it, but I think this would, at this stage, be considered inhumane. The sublemma says that if G is acceptable, then the number of triples that intersect it oddly is at least the number of vertices in G times the number of edges divided by 3. And this is tight. It's really not difficult. I mean, with a 4 here, it's a few lines proof, but I will save it to you. Why? Let me only show you that this is tight. So you take this tripartite graph, or whatever you want to call it. The vertices are partitioned into 3 equal parts, and the edges are just all the edges that connect this and this. So it's very easy to see that this is acceptable. This graph is a minority in every cut that you take. So let's calculate. The number of vertices is, of course, n. The number of edges is n squared over 9, right? Everyone here times everyone here. And what is B of G? Let's think about it for a moment. Which triples meet the edge set of this graph oddly? So first of all, this graph contains no triangles. So meet it exactly once. So it's exactly, you take one vertex from each, and so that would be n over 3 cubed. So this is n over 3 squared, and you see that this is precisely. So that's a key step in the proof, but there is much more than that. But okay, so the main thing is that we got the exact answer very accurately. Okay. Okay, so
Why is it sufficient to restrict yourself to acceptable graphs that just...
because we don't care, the trivial vectors in the left kernel we completely ignore, right? This is I mean, if you give me a vector and I modify it by a trivial vector in the left kernel, that doesn't change anything. So for this whole collection, it's enough if I select one and I concentrate on this. And the one I select is this particular one. So okay. Good. So this is more or less, except for that we'd like to really get this thing completely nailed down. We'd like to eliminate this O. This is still an O. This part is more or less a closed story. But there is another part of this theory where really the mysteries are still huge, and it's really wonderful, and we're still working on this to that very moment. So let me try and tell you this. So again, coming back to Erdős-Renyi, the most exciting discovery, I think the most important discovery which they didn't even spell out in this generality, is this threshold phenomenon. And the most exciting is the phase transition at p equals 1 over n, which I'm now going to tell you. Please.
Is there an interesting problem here where the coefficients are real?
No, it's the same as, yeah. Okay, good. So
But so the threshold does not depend on field at all?
this is the conclusion. It wasn't clear a priori, but in hindsight, this is what turns out.
But even for greater than 3, like if d is greater than 3?
No, same thing. Same thing.
What's the matrix? So what do you put? So because you had to change. So once we work over a field that's not characteristic too, we had to have about one.
Yeah. We need this. So that requires orientation. So you orient.
Oh, so you orient.
You orient all the simplices and you put plus and minus according to whether they're consistent or not. So that's one reason why I evaded this here, because that is a small headache that you have to go through, which you avoid if you go in the field with 2 elements. But if you want to hear about this, I'll be glad to explain.
Yeah, the only thing I would just, I don't know, just that's striking me here is that you basically, what the problem is now, we pull a random subset of columns from a matrix A that we're sampling uniformly at random, and we just want to say, when does the kernel coincide with the kernel of the original matrix? So it's very much like one of the matrix concentration inequalities, but I don't know if those don't work over GF2.
Over finite fields. No,
Yeah.
Is there such a connection through this? I don't know, but that's right. Okay. So perhaps the most exciting discovery in this early stages of the theory of GMP was the phase transition at p equals 1 over n. And if you never saw this, I highly recommend it. Okay. So again, it's easier to look at these things within the evolution of random graphs. So you have n vertices and you start throwing edges at random and ask yourself, what is the structure of connected components? What do the connected components look like? So, and there is really a fascinating thing which has been investigated in great detail and in great depth, which occurs at this point. So there are really tons of papers on this, and we now understand this really, really well. But for the purpose of a relatively shallow discussion, if P is 1 minus epsilon over n for any epsilon positive, then G consists of small, simple, connected components. So small means all of them are at most of logarithmic size. And simple means they are mostly trees, with the possible exception of a constant number of a unicyclic, so tree plus an edge. So very simple description. What happens around p equals 1 over n, and p is 1 plus epsilon over n, then very suddenly a giant component emerges. So a giant means of cardinality omega of n. And that's a very interesting thing, how this thing happens. And lots of interesting and surprising phenomena happen at this point. In particular, and this we would like to understand also in higher dimension, and this, at the moment, we only have a partial understanding of this, and I'll describe to you a little of what we know. So in particular, you ask, is a function of p what is the probability G that we sample from G and P contains the cycles. So if P is 1 minus epsilon over n, then there exists a C of epsilon such that this probability is less than 1 minus C. There is still a positive chance that it's cycle free. But once you have passed this point, then everything is, then almost surely the graph already contains a cycle. Now, the advantage of okay, let me just say this. One thing that's obvious, and we have only very initial guesses about this. I'll show you something that we see experimentally, but at the moment we can't prove. I should start here. What is the giant component in higher dimensions? So we don't understand. Let me just say this very clearly. We don't understand, but we are starting to feel this animal, what this is, and we have some early hints, but at the moment we certainly don't know how to answer this. So we try to go around this and ask questions that we are at least able to formulate within our framework, and then this will allow us to at least get started on the problem. So where do you see, again, so we now already saw that linear algebra is a good guide in formulating the problems and looking at this. So when I give you the incidence matrix of a graph, where do you see the cycles? So the cycles, this is A, cycle space is exactly the right kernel of A, right? Because if I multiply here by a vector of zeros and ones, this means I've selected a subset of the edges. And the fact that it's 0 means that every vertex has an even degree. So the basic things are cycles where vertices have degree 0 or 2. So this is something that we can ask. So this allows us to, at least to formulate this question also in higher dimensions. So this suggests the following question. Again, I will formulate it just at d equals 2. What is the critical P? By the way, this model that we call it in general X, D, N, and P. So d equals 1. This is exactly G and P. What is the critical P in X, D, and P for there being a non-zero right kernel? So these, in the case of if d equals 1, we know the critical P is 1 over n. Now let me take you a little bit to the more conceptual side of the story, and then let's think a little bit more about what this means. So, in other words, what we're asking here, being a cycle free means being a forest, right? So, same as probability that G is a forest. And so the conceptual thing is that the analog of this in higher dimension, there are many more options which are interesting. Let's discuss them a little bit. Okay, so you all know the very simple proposition, the following simple proposition from graph theory. Let G have n vertices and n minus 1 edges. Then the following are equivalent. 1, G is connected. 2, G is acyclic. 3, G is collapsible. So the first two, of course, you know. The third, you know, but I'm not sure that you know that you know. So what is collapsing? Collapsing is this. You take a vertex of degree 1, and you eliminate both it and the edge that touches it. Okay? So collapsing means that if you keep doing this, you're eventually remaining with no edges. You eliminate all the edges this way. So of course all the three are equivalent. But now we know we have a language of formulating these three properties also in higher dimensions. So let's see what they are. So the analog of this should be a no non-trivial left kernel. This is no right kernel. This is again collapsible, so I have to explain what collapsible is. I'll explain it just in 2 dimensions. So here what did we have? We had a vertex, a 0-dimensional face, that was covered by exactly one one-dimensional face. So in 2 dimensions, if you have a 1-dimensional face, an edge, that is covered by a unique face, then we call this edge free. And a collapse means that I throw both of them away. Okay. Now, topologists will tell you that collapsing. So collapsible means that when I do this, I eliminate all the faces. So topologists tell you that the topology of a complex doesn't change as a result of collapsing. So you might think that the same thing holds in general. No, so it's very easy to show. It's all that in general 1 and 2 are equivalent. 3 implies 1 and 2, but it's not equivalent. Okay, and so this now suggests 2 concrete questions to ask. One we already solved. One we have only a partial solution for. So question 1, what is the threshold for collapsibility? In X, D, and P. Question 2, what is the threshold for the vanishing of the right kernel? Okay, so these are things that I studied together with my student Lior Aronstam, with Roy Meshulam, and with Tomasz Wuczak. So this question we got completely. We know the answer to this. This question we got only partly. So in particular, so
Are the thresholds different?
they're different. Okay. So here I'll tell what. Here's what I know as a person, and here is what I know as a mathematician, which are not the same. So the answer for 1 is P is, let's say, alpha D over N. Alpha D is very close to log of D. And that is a full answer. For 2, we know that P is less than or equal beta D over N, where beta D is 1 minus little of 1 times D. But we are unable at the moment to even tell. We don't know how to get a lower bound for 2. We can't even at the moment prove that these 2 things are not identical. And here we're using all sorts of machinery from much more advanced stuff from random graph theory. Just not to overdo it, let me spend another few minutes on the notion of a tree, and with that I will finish. So there is a very nice paper from 1983 due to Gill. Where is it? Disappeared. Yes, please.
Is there any other interpretation of collapsibility? So it implies these things, but
Right.
is it equivalent to something else we can think about?
Collapse, you see, okay. They are this is a completely combinatorial condition. And therefore, we had much more machinery that we could use. And therefore, we were finally, there was a paper of the four of us where we got a lower bound on this. And then with Aronstam, we got a matching upper bound and we closed this thing. Here, I mean, it's a little shameful, and luckily no one of you asked, but I will ask myself. Doesn't the answer for this depend on the field? I probably tired you already enough in the first things. People asked field, and I said, no, not important. So people are now perhaps discouraged, except for Brave Mario, Super Mario. No one would ask this, but it's shameful, but I'm not even sure I know the answer to this. So many things here I know as a person, as I said, because we experimented quite a bit with these things, but some things I can prove and something we can prove and we can't prove. If I have to guess, then the answer here also doesn't depend on the field, but it's still more, but actually before telling you about these trees, let me just show you one little thing from simulations, which is really nice. This is why. Before my other friends call me on Skype and so on, and my wife is looking for me. No. Is it? What would I do without Guy? Okay. Okay, so that you saw. But in fact, let me remind you, because this is a good reference to. So again, what did we do here? This is the situation in graphs. You have n vertices, you throw edges one by one, and you ask, Gil, you came back on time. I'm about to speak about you. I didn't know where it disappeared. And you ask, what is the chance that this edge connects two connected components, or doesn't? So this is okay. So how do you see in linear algebra about connecting two connected components? Does the rank go up? If you think about it for a second, you'll see it's independent. So initially the rank, each time you add a column, the rank goes up, then it starts going down, and eventually, now let's do the same thing in 2 dimensions. So again, what do I have? I have a complete graph on n vertices, and I start throwing in faces, triples. And I ask the same thing, is the rank going up? You've added the column to the matrix. So the rank can either stay or go one up. And see what happens. I find this really amazing. This is the kind of picture I can look at for hours. What is this sharp threshold? Think of it, it's pretty amazing. And we still do not understand what is going on, but we have some more than initial intuitions. We are not completely in the dark. I mean, if you came to me half a year ago, I would say we are essentially in the dark. No, now we, together with another excellent student, Yuval Peled, we are now starting to understand this, but we're still far from having a... But let me explain why this is so amazing.
So what do we see here?
Okay, so again, let me see. So n is 100. We have 100 vertices. You have a complete, and you're generating such a matrix of 100 choose 2 by So initially it's as skinny as it gets, no columns. And each time you pick a triple, you pick and you add it to the matrix. Okay. Now when you add, initially of course the rank is 0. Each time you add a column, either the rank stays or goes up by 1. And here, so it's repeated, I forget, 100 times perhaps. What is the chance that on step 5322, the rank goes up? So initially the rank goes up each step. And then there is this sharp drop. So what happens here? Think about it. You have a matrix which so far you've been able to add things to it and they're linearly independent. And then all of a sudden, so what I'm calling your attention to is the sharp threshold as opposed to the relatively relaxed threshold that we saw for graphs. All of a sudden, every new column that you add, every triple that you add, creates a dependency. So just among Yuval and myself, we use this metaphor. It's a dream catcher, that's what we call it. You see, you have all these triples, no bemet. Go home. You have it's such an amazing object. It's a simplicial complex, a two-dimensional simplicial complex that capture everything that comes through, which previously, just beforehand, nothing was captured. We still don't understand this. This is, as far as I can tell, the best description that I have at the moment. I can tell more, but all of this is conjectural. We don't have proofs at the moment or anything. This is what happens. So you see, the whole behavior of the appearance of the first cycle in one dimension and two dimensions is completely different. In a graph, we understand exactly the length of the first emerging cycle. So again, you start with n vertices, you throw edges, and you look at the first moment that the cycle was created. We know the distribution, how long it is in 2 dimensions, and that in fact we proved. That we proved in work with this trio, that either the first cycle that you create is either the boundary of a tetrahedron, or it touches all the n vertices. It's quadratic in size, sorry. We only know, formally we only know quadratic in size. Experimentally, touches all the vertices. So the two things behave in a really radically different way. So there's really completely different behaviors, which at the moment we only are starting to understand. Let me just briefly and finally, I think you've suffered enough. Yes?
Say to that picture that
Yes.
it's not that it catches everything. It catches everything means probability 0.7.
That's right, absolutely.
So
Yeah, you're absolutely right.
You add the 4,000.
You're absolutely right. And we also don't understand. You're absolutely right. That's right. The drop wasn't all the way down, as Mario observed. It was to 0.3. And it's easy to explain 0.18, but there's still 0.12, which I don't know how to explain. Now, the whole thing is really very mysterious. It's one of the situations. I'm a great fan of experimenting with the computer, but that's one case where really the computer shows you things that, leave me speechless. So
The picture is the same for a different field.
this was done only GF2. I don't know. So let me just very briefly tell you a few last comments on trees. So of course trees are also a very fundamental combinatorial object. Here the basic definition is due. He's here. Okay, Gil from 83. And he looked into something like this. And he asked, so now you have a full, that's a full D-1 skeleton. And you ask, how many D faces can you have here and still this is going to be, so the rank of this matrix, that's is n-1 choose D-1. That's very easy to prove. N-1 choose D, sorry. And so the right definition of a tree, or hypertree, or QA cyclic complex, that's what Gil introduced. So a hypertree, a D hypertree, is a set of n minus 1 choose d faces such that right kernel over the rationals is 0. That's its definition. And these things are very interesting. You can investigate them. Let me just give you a one. They're very different than what we're used to think about trees. You can also take as a definition that it has this many d faces and it's collapsible. That would also be an analog. There is really a lot of different possibilities. But let me just tell you a small thing that Yuval Peled and I have discovered. This is proved already. That's not just experiments or anything.
So Nati, so to that your picture.
Yes.
So it's why is it like kind of 3,000-4,000? So you are saying the graph, the hypergraph has 100 points.
Right.
So what you expect, well, if it's 100 choose 2.
No, it's C over n. It's that C which I mentioned before, C over n times n choose 3. This is where the drop is. Okay. The same C that I mentioned before, which is close to D, etc. Okay. So just to illustrate how different these things are, and there's still an interesting choice to, what should we consider as the most interesting, or perhaps there are several interesting definitions of an analog of a tree. So let's say you have in a graph an almost tree. So this means n vertices, n minus 2 edges, no cycle. Now, at least half of the edges are in the shade. So, what do I mean by this? This such a thing has two connected components. Such an edge, I call it in the shade if it connects, and this is not in the shade. If you think about it, how do you minimize the number of edges in the shade? You make these two things equal. Okay. In contrast, so with Yuval Peled, there exists a two-dimensional almost tree with no shade, zero shade. So what does this mean? It's a simplicial complex, a two-dimensional simplicial complex. It has n minus 1 choose 2 minus 1 faces. And every face that you add to it, you get a Q hypertree.
You get that?
A Q hypertree. Being in the shade means that when you add it, you don't get a tree. In this example, everything that you add, you get a tree. These things are completely different, very mysterious, very fascinating. I think you suffered enough. It's time to stop. Thank you.
Questions? Just a brief question. So in the previous talk, the idea was that to go into higher dimension, we took things that we associated as matrices and then turned them into boxes, hypercubes, hyperarrays. Here, while we move up, we're still putting everything back into matrices, right? We just said it's always one dimension down. There's probably no connection, but I'm just kind of curious as to is there a reason to avoid something?
Okay, so
Boxes.
I'll answer a different question if this is okay with you. But I think perhaps the spirit will. So one thing that I was asked, especially people who like algebra, I ask after I speak about these permutations, what I spoke in. So there is one very important aspect of permutations that didn't exist here. Permutations, of course, form a group. There's a symmetric group. So is there an algebraic structure as you go up? For all I can tell, the answer is negative. And in general, I can say that one of the nice things about combinatorics is it seems like much more robust part of mathematics than most parts of mathematics. It survives in the desert, on the mountains, wherever you throw it. High dimension, low dimension, it's okay. Algebra is more gentle. It needs some special conditions to And this is, I think, what you're seeing here. So it's very easy to develop the combinatorics as you go to higher dimensions. And all the supporting terminology. So this, of course, these matrices, of course, we didn't make them up. They come up, if you think about these things from the topological perspective, these are D minus first homology, D homology, all these things are there from the topological perspective in a very natural way. So here we don't create anything new. We just follow the existing, the questions. These questions speak about the vanishing of the D minus first homology, the first set, and the vanishing of the D homology. So in this respect, we don't try anything new. We follow the known there.
So, I mean, in this talk you used basically linear algebra concepts to define a lot of these things, but in the previous talk you said that defining expansion for higher simplicial complexes, you said that the spectral thing doesn't make sense.
No, it doesn't make sense. No. Many people that I know, strong people, are attempting to develop the theory of expander graphs to higher dimension, trying to use spectral techniques. I'm not a great believer in this. I think that when you want to go with the expanders to higher dimension, the right thing to do is to understand random, regular, simplicial complexes. And that's a huge challenge. And then that would set the standard. So we know in many different ways that a random regular graph is expanding just as well as possible. So if you understand how much it expands, then this sets for you the standard for what you would be calling a good expander for graphs. And this, I think, is the analog, but at the moment we have so many things missing. I didn't even get to speak about this. The concept of regularity in complexes is fascinating. We know close to nothing about this. There is really still a lot of theory to develop there. There is chance for a lot of fun to be had in high dimensions.
I was wondering about the algorithmic implications of going up in dimensions. So for instance, in the first talk you showed that for two-dimensional permutations you don't have Birkhoff's theorem. Right. So you cannot optimize over them easily, etc. So is this something general that you see, that when you go up in dimension?
You see, I mean, any theoretical computer scientist would tell you, that going from 2 to 3, you go from the settled land to the desert, right? I mean, 2 CNF is so easy, 3 CNF, forget it. But we are still not giving up, right? I mean, people are studying it's hard, but it's not hopeless. Here, I think, while, this is honestly motivated, at least to a large extent, by what I said at the beginning, that we will need this kind of combinatorics if we want to deal with situations where interaction is not pairwise, but the algorithmic, I'm afraid we will have to wait a while until we understand anything about this. I'll be really glad to see anything along these lines, but as you see, the difficulties are still very big.
So sometimes in math, when especially feels like topology, where 2 and 3 is hard and hopeless and 10 is out of sight, same time as 1,000,000 is feasible. Is there any notion of asymptotic, large, really high-dimensional phenomena that still survive?
It's not impossible. There are certain things. For example, not that perhaps Gil probably understands these things better than I do. But for example, Poincaré's conjecture, right? I mean, somehow 5 dimensions and above. So here I'm saying words that I don't really understand, but I can at least say the right words. 5 dimensions and above, there is one proof that relatively, I think now for topologists is considered not so difficult. And as you went down so special phenomena that occur in low dimensions is something that is completely commonplace for topologists. And I wouldn't be surprised if we discover such things here as well, but we haven't so far. So it's not impossible that when you really go up in dimension a lot, then perhaps certain things become in some way simpler. It's not out of the question. There is a whole subfield of topology, a huge low-dimensional topology. People work in low dimensions. It's a
All right, thank you, Nati. We have a break, and Ravikant will bring us home.